Okay. About radiometry and apparent optical properties, I think you have had a number of lectures already on inherent optical properties. So I guess that's a logical next step. As Shubha said, before I start, a quick summary of who am I. So I got my PhD in oceanography, January 1995. That was from University Paris 6, Pierre and Marie Curie. And I did this in the Villefranche optics groups under supervision of late Professor André Morel. So, well, I became, as is said on this slide, CNRS research scientist in 1996. Oh, very good. CNRS is the French National Research Institute. Well, I started my career there, progressed to a senior research scientist in 2008, started to move a bit around by doing a one-year sabbatical in the US at UCSB with Dave Siegel's group. And finally ended up in Australia. That's actually now 11 years ago. Hard to believe, but that's what it is. I am a professor at Curtin University, which is in Perth on the western coast of Australia. That's the only big city in Western Australia. And I'm leading the remote sensing and satellite research group there. So along these many years, well, as you probably know, I did some work on the satellite ocean color, roughly speaking, and starting with more of a modeling approach and profile, in particular modeling primary productivity from space, from ocean color, working on atmospheric corrections, and then moving a bit more progressively to adding a bit more of the field optics. And that's in particular when I started to develop 23 years ago this very long-term time series called Boussole in the Mediterranean Sea. That's unfortunately a project that has come to an end at the end of last year, but that's still one of the longest time series, and there is still quite a lot we will be able to do with this. Along this way as well, as Shubha reminded, I've been quite significantly involved in national, international bodies, committees in charge of coordinating science, defining satellite missions, and so on. And I've continued to do this since I'm in Australia. On a more personal basis, so I'm now 59. Got married some time ago, 1990. My kids are grown up now, away, 25 and 30, they're their life, in Australia with us as well. And my hobbies were, I was quite a serious sailor when I was young. Then I became more occasional, and now I'm no longer doing any sailing, just a bit. I moved to cycling, and I'm now quite a regular cyclist. That's more or less all about me. You have these two websites on this slide, and of course you will have all the slides. The one on the left is the website of my current group, and the one on the right is the one of the Villefranche Optics group that you probably know as well. Okay, and well, just a few pictures. I could have added maybe a few more recent ones, but of a number of environments I have been working on. So, doing some measurements from the Arctic to the on the southwest, on the bottom left corner of this slide. It's things we did recently, just 2 years ago, in the northwest of Australia. As you can see, the kind of wildlife is a bit different. And the one on the top right is again in the Arctic some years ago. One thing I should mention is maybe at the moment we are focusing not on the Arctic actually, but on the Southern Ocean, and that's quite a lot of our activities at the moment. Okay, let's go to the lecture itself. So, well, that's a quick content. So we will progress progressively from linking AOPs, radiometric quantities, and AOPs. There will be a bit of about terminology, calibration, defining main quantities, and so on. And yeah, of course, there is one reading reference at the bottom of this slide that you probably as well, most of you know. That the Ocean Optics book by Kurt Mobley and many others. It's online, and there is, of course, a lot that you can continue to learn by going there. Yeah, and a few others that I added on that slide. Okay, and well, I'm going to skip this one, but that's included in the series of slides, so you can look at all this additional reading source if you need. So we'll start with this complicated scheme. That's a figure from Kurt Mobley. He called it the Ocean Optics organizational chart. That's kind of interesting. So let's start, with this different part. I think it works. Yes. So what you have seen so far, inherent optical properties. So the absorption coefficient, volume scattering function. They define everything. You can integrate the VSF in different ways. You get as you know now, the total scattering coefficient or the back scattering coefficients. Then you have absorption. You can calculate attenuation and all sorts of derived quantities. That's all the inherent optical properties. Well, but then this is not happening in the vacuum. That's in a medium, and then you have boundary conditions. So for what we're interested in, ocean optics, so that's the sky radiance above the surface. The sea state, which is defining how the interface between the atmosphere and ocean is going to be, flat or often by waves. You may have the sea bottom if you work in shallow water. So this is another of the boundary conditions. Forget about it if you're working in the deep oceans, of course. And you may have as well some internal source, bioluminescent, fluorescent, whatever. So they are considered the boundary condition of your problem. So this is then defining inputs and context of radiative transfer in this ocean atmosphere medium. And that's, as you know, expressed through the radiative transfer equation. Radiative transfer equation, there are many ways to express it, okay, depending on the type of geometry you consider, depending on the application and so on. Okay. So the one you have here is just one example of expressing it. The nice thing is it's relatively intuitive that it tells you that, okay, with L being the radiance, we are going to get to this in a minute. So the change of radiance along a given path, okay, is equal to the attenuation of this radiance along the way, along the direction of propagations. And actually, this equation, you see the C here, which is the attenuation coefficient. Okay, you can move it on the right side of the equation, and that's a bit more readable, I think. So you would have this minus CL, which is basically telling you how the radiance is attenuated along the way in a given direction. But then you can imagine in the medium, you have radiance coming from all sorts of directions, and they can be scattered in the direction you are interested in. And that's what the other term is expressing simply. And then you have this beta, which is the volume scattering function, or the phase function if it's normalized to the C, which is the case. Okay, so just basically these two things to keep in mind. There is attenuation along the way, but some addition of radiance from scattering from the other directions as well. And that's going to then define the radiometric quantity at any point in the medium. It could be as well at any time, but all these things that I'm describing at the moment are considered expressed in a time-independent way. So you end up with scattering, absorption in all directions, or you have a radiance field or radiance distribution, so radiance coming from all over the space. So that's this L, and it's called L. That's actually coming from the French word for radiance, which is luminance. There are a number of things like this in physics, where the symbol is using actually the first letter of a word in some language. It's not always English. It can be French sometimes, but okay. So L is for radians. And again, you see that here it's as a function of Z, the depth. Whoops, this mouse is moving so fast. Theta, which is the zenith angle. Phi, which is the azimuth angle. Generally, the azimuth is expressed in terms of difference between the azimuth of your viewing direction and the azimuth of where the sun is positioned. And as a function of wavelength lambda, of course. Then you can integrate these radians in all sorts of ways to get to other radiometric quantities. And a few of them are expressed here in this slide as well. So downwelling scalar irradiance, you integrate radiances, all the radiances coming from the upper hemisphere, but you don't consider their angle of incidence. So you can imagine the energy coming onto half of a sphere on the sphere. Downwelling plane irradiance, that's when you will start to consider the direction of propagation and then the impact it has on how much energy is coming onto a plane. So that's where the cosine of the view angle is going to, the cosine of the view angle is going to be important. And you can do this, of course, for the upwarding hemisphere as well, or for the entire radiance distribution to get the full scalar or vector irradiance. And then if you have all these radiometric quantities or variables, that's how you can derive the apparent optical properties. So that's so far in this lecture, that's the main message, the main thing to keep in mind. Radiometric quantities are one thing and apparent optical properties are something else. And what you measured when you go at sea or when you have a satellite, whatever, they are radiometric quantities. You don't measure the AOPs. AOPs are derived from the radiometric quantity. So, well, not wanting to be pedantic about this, but that's an important distinction. And when you write in the paper that you have been going at sea measuring the diffuse attenuation coefficient, well, that's not really correct. You have calculated it from some radiometric quantities, and in that case, the downward irradiance. Okay, so in this green box, you have all sorts of these AOPs. So one of among the most popular or known is the irradiance reflectance, or the upward to downward plane irradiance. Actually, it's interesting because Kurt didn't even include the other one, which is one of the most used at the moment, which is the remote sensing reflectance, which is the water leaving ratio of the water leaving radiance to the downward irradiance. So that would be LW upon D. You can calculate the average cosines of this light field, which tell you about the directionality more or less of the light field. And of course, all the K coefficients, or the diffuse attenuation coefficients for the downward irradiance, for the upward radiance, for whatever quantity, whatever radiometric quantity, you can associate a diffuse attenuation coefficient to it. Oh yes, of course, the remote sensing reflectance is in this slide. Okay, tomorrow I will be in better shape, I guess. Okay, a bit of terminology. Well, I'm not going to go too much into it. It's just there so you have the reference. It's not a particularly recent reference, but the terminology in these things has been defined. It's physics, and it doesn't change every year. So this is still completely valid. So this slide and the next one, I think, are telling you about how to express these radiometric quantities and AOPs and what are their fundamental units in the SI system. And okay, we get here the one in the middle, so the one which we use the most, so the radiance. And you see between the brackets is the French equivalent, luminance énergétique. And so definition, radiant flux in a given direction per unit solid angle. We're going to look at this. And per unit projected area. So you have the units, generally watts per square meter per steradian. And the steradian, which is going away when you integrate, of course, to calculate the radiances, the irradiances. Sorry. The geometry of the problem. Which is the one we use, for the remote sensing application, but as well for field radiometry. So always with three angles to keep in mind. So the sun zenith angle. So because that's the source of energy for our problem. So the sun zenith angle, which is generally denoted theta s or theta 0, depending on which paper you're going to look at. The view angle, so in that case, for view angle of a satellite, so theta, so but that can be the view angle of an instrument you're deploying from a ship or whatever. And then again, this azimuth difference. So if you consider the azimuth of the sun starting from the north, counted clockwise, you may have some kind of value. So maybe the sun is at 90 degrees from the north. And then your instrument, satellite or ship-based, is pointing in a given direction. And that's, again, another azimuth value from the north. And the difference of these two is the azimuth difference. And that's the angle that there are the three triplet of angles that allow you defining the entire system. From that, there is a few other definitions. So there is one which is called the scattering angle. So this one is, again, so a function of all these three angles, sun zenith angle, view, and azimuth difference. So that's basically, telling you the absolute, our given radiance is going to be scattered back. And the solid angle, which is important for the definition of radiances, which is basically the small cone, some way, in the entire space that you consider for the where your radiance is coming from, and you have all the definitions here on this slide. So that's bring us to the radiance, the fundamental quantity, which is expressed here. So again, here what we have, this delta Q over delta T, that's the radiant flux. This delta omega, that's per unit of solid angle, so this small cone of space. And the delta A in that equation, which is per unit projected area. And the delta lambda, which is because it's a spectral quantity. So that's, oops, sorry. Okay, that's again the radiative transfer equation, which is coming on this slide. But on this one, you see that the C attenuation coefficient has been moved to the right-hand side of the equation, which is making things a bit more, at least to be intuitive. An important property of radiance is what is called the radiance invariance, which means that the radiance is independent of distance. You look at the measure of radiance of a given object or medium. If the radiance field is homogeneous, and that's called, the target is called a large étendue. Sorry, it's again a French word which has been carrying its way in the physics world. So it's independent of the distance, okay? So you can change the distance between this homogeneous invariant target and your sensor, and you get the same radiance. So that brings us to radiometry, and radiometry is simply the science of measuring electromagnetic energy, so optical radiant energy, so measuring radiance basically in a given medium. So what's written here, basically you need to collect energy, transform this into a signal that you can measure and quantify. But as well, you need to have units attached to this as for any physical measurement. So you need to calibrate this to some kind of standard. So you need reference. And so that's bringing us to the question of what are the units and standard for radiometry. You know, if you go on the websites or the documentation that the National Institute of Standards in the US or anywhere in the world are providing, so you can look what are these SI base units, or you know, the meter, the kilograms, second, and so on. But then, you know, that's doesn't intuitively speak much as to how these things are connected to a radiance. And other of these quantities are the one defining these angles, like the solid angles and so on. So again, this is the equation we have seen before. And if you consider if you go back to the, you know, the basic definition that's were in this one of the first few slides, and you look at what are the units of the radiant flux, of the solid angle, wavelength, and so on, and you combine all this, and you end up with this watts per square meter per steradian and per unit of wavelength, nanometer in that case. So that would be micrometer or whatever. Okay, well, sorry, that was the same thing we saw before. Okay, now, you know, standards in physics are, of course, very important, and there are a number of them which are relatively obvious. I think the one I have put on that slide are the standard for the kilogram and for the meter, which are kept, I think they are kept in Paris at this BIPM you see on the website is Bureau International des Poids et Mesures. It's again another French acronym. It's kind of the equivalent of the NIST. But, you know, what about radiometry? What's the reference? So that's a bit more sophisticated or complicated, just a piece of some metal that has been defined for the kilogram. So the primary standard for, you know, any of the, if you have been using in your work so far, you know, instruments like a radiometer you deploy at sea or whatever, they are all at some point connected to this primary standard in some way. And this system, so it's called the cryogenic radiometer. So it uses a technique which is called electrical substitution technique. So I'm just reading what is written here, but there's another slide just a bit after, which is maybe a bit clearer. So whereby the optical power incident on an absorbing cavity is compared with the electrical power that you would need to heat the cavity at the same temperature. So then you can connect radiance and electric power. That's where the watts per square meter and so on come from. And it's called, the cryogenic. It's just because this entire system is kept at very low temperature to improve sensitivity. So just an example on the left, the one which is used at the UK Institute of Standards. So basically, that's another way to express this. So you have, you know, on the, if you look at the graph on the top, so you have a given optical power coming onto this receptor, and on the other side you have you try to match this the increase in temperature that your optical power is going to generate by electrical heating, of the same device. Okay, and that's how you get to the watt per square meter per nanometer. But of course, not all of this instrument I mentioned before that you have been using is going to be directly connected to this. Only National Institute of Standards have this kind of technology. So that means generate what we call primary calibration standards. And then this primary calibration standard might be used to calibrate secondary standards, which are less expensive and available for maybe the manufacturers of instruments to be used. And then the manufacturers of instruments are going to base their calibration on this, plus they are going to transfer it to their own calibration systems. So that's where I guess you can start to see that, some uncertainties can happen in a process like this when you transfer calibration from different standards. But at some point, everything is going back to this one. Okay. Another thing, another important thing for the calibration of instrument we use in marine optics is, of course, they are all calibrated in the lab, in air, and they are deployed in water. So that's why we need to apply to them what we call immersion factors. And again, generally, that's embedded into the calibration file you get from your manufacturer. This is in there. So quite often people just do not really realize actually there is something like this. For radiance, it's entirely a function of the difference of refractive index between the water and the material of the window that is used to collect the light. So that's the equation you have on the top. So you can calculate this if you know well enough these two indices of refraction. You can calculate this. For irradiance, it's a bit more complicated because, and you have a graph, a small plot here, which is trying to express this. You probably know this instrument, you collect light on the diffuser. So collecting light from all directions, integrating this and transferring to your detector. But then again, how the incoming light, part of it is going to be reflected from the diffuser actually, or the light which is getting into the diffuser might then get out back. So all the refraction effects between the water and the diffuser are not going to be the same as what they were in the air. In that case, it's a bit more complicated to theoretically derive this. So it's generally derived experimentally in the lab. So generally what is done is it's a complicated thing to do and to do it properly, but the sensor is put in some sort of a tank in water, and you get measurements from a number of different water depths above the sensor. And by extrapolation, you can try to derive what this immersion factor is. One thing you have to know is, we will come back to this tomorrow in the uncertainty lecture, but it's a complicated thing to do. And manufacturers do not like to do complicated things because that's expensive. So they generally do it once when they build an instrument and they are going to commercialize this instrument on the market. They might do these kind of things. Sometimes they don't even do it. They take, a good guess. If they do it, they will do it once, and that's the number they will give you in all the calibration files you have. But of course, if they build 100 of these different instruments, each one is going to be a bit specific. And actually, if you would like to really be very accurate, you would have to redefine this coefficient to experimentally on each and every of these instruments. So that's another possible source of uncertainty. We will go back to this tomorrow. So measuring radiance. It's basically the way it's done, whatever the technology is behind, but basically you have to collect light in a small angle and to bring it to a detector. So this illustration here, which is again coming from the Ocean Optics book, is the one of what is called the Gershon tube. And so you can see here that the aperture here and the whole design is defining this solid angle over which you're going to make your measurement. And well, you know, all of this, you generally need to avoid all sort of scattering, reflection, and so on in your instrument. So that's what this light baffles are generally used for. And then you have your diffuser and your detector. Okay, that's basically what any instrument will do, with of course different technologies. And so now we're going to have a look to historically how this has been done. One of the most amazing things that has been done actually was 1960. That was a long time ago, but with the technology they had at that time, it was really a brilliant experiment. So by Tyler, 1960. So that's one of the first, if not the first, underwater radiance distribution that has been measured. So you have the instrument on the left side. You can imagine, you see at the end here, you have a rotating system. You have two Gershon tubes, and this thing is just rotating. So taking measurements in all directions in a given plane. But then they had this possibility with the fin here to orient the entire system. I guess that was probably a bit complicated to do, but they did it. And then they could do it for, you know, making these all measurements in the plane, looking at the sun, and maybe some 10 or 15 degrees away from the sun, and so on. And that's what you have on the plots here on the right side. So each of these plots is for the radiance, so it's a log scale. And each of the curve is for a different depth. And the one on the left is in what is called the principal plane. So that's the plane containing the sun. And the one on the right is the perpendicular plane, which is 90 degrees away from the sun. So of course, in the principal plane, you have this peak, which is basically the radiance coming from the sun directly. And as you can see, you know, it can be 1, 2, 3, 4 orders of magnitude larger than the radiance you have on the slant directions. Yeah, because sorry, the horizontal axis is the view, the view direction. So, and you can infer from that the sun was probably something like 20, 30, or 40 degrees in the sun, in the sky. When you move on the perpendicular plane, of course, you no longer have the image of the sun, so you have a symmetrical distribution this radiance. Well, some of you might be well known to this. For others, it's a good way to, you know, look at these kind of things to figure out, you know, when you make measurements at sea, for instance, to get a good feeling of what the radiance distribution is underwater and what the main parameters are driving it. So 1960s. It's a jump of 50 years. Yes, 2011. Quite a lot has happened in between. I'm just here putting some examples where to try to get to this as much measurement in as many directions as possible of the underwater light field. So that's an interesting instrument that was developed by Dariusz Stramski and his team. Well, basically, they have developed, you know, a frame, and they have put these radiance sensors in all sorts of different directions. So they could have instantaneously the measurement of radiance from many directions. They were actually, well, they were measuring irradiance as well. And one of the purposes of this one was to look at in particular, to look at the very high frequency fluctuation of radiance and irradiance just below the surface because of the interface roughness. And what you have on the right side of the slide are, you know, just recordings from these instruments. You have the condition of the sun zenith angle, 20, 25, whatever. Well, the only thing to keep in mind of this one is this very high frequency variability, which is always what you have when you measure downward quantities in particular, downward irradiance, or radiance from the upper hemisphere, relatively close below to the sea surface. As soon as you have a bit of wind, a bit of capillary waves, you will have this very high variability. And that's something to always, of course, keep in mind when you do radiometry measurements at sea. That's a big constraint on how we can do them. Another way to get to the full radiance distribution is to use a camera with a fisheye optics, and then you collect instantaneously light from all directions. And you move this to a detector, and you get an image of this. So that's something we did. That was, 2013, so quite a bit of time ago as well. So we developed this radiance camera, but the Ken Voss team at University of Miami has done quite a bit of this as well. And then you end up with this kind of distribution. So what you have on this polar plots is at the center of each of these plots, it's the radiance coming from nadir. Then when you move to the periphery of this plot, you progressively move to the radiance coming from horizontal directions. And the azimuth is the third dimension of this plot. On the vertical, it's for several wavelengths, starting on the top at, it should be on this slide, yes, 406 nanometer, and so in the blue. On the bottom, it's in the red, and this 1, 2, 3, and 4, the 4 column, are for different types of environments, from clear for 1 and 2, but with a very different sun zenith angle, and then to moderately turbid to highly turbid waters. So without going too much into the description and details of this, well, what you can see first is the very wide range of values, because the scale is the same for all these plots. So, top right, you have extremely low radiances, and that's because of strong absorption in these very highly turbid waters. A maximum in the green. If you go in the third column, this red orange color for the green bands. That's typically what you have in the turbid waters with increase in the green, and so on. What you can see as well is the heterogeneity of this distribution. Okay, so sometimes it has a tendency to become relatively homogeneous, azimuthally speaking, like in the one at the top right. And it all depends, again, on the geometry, where the sun is in the sky, and the inherent optical properties. So if you have, for instance, a lot of scattering, sunlight is going to be redistributed a lot in the water. So the light field is going to be less and less structured and moving progressively to a nearly isotropic homogeneous field. That's nearly never happened actually in the oceans, but that's the direction the light field is taking, from being very structured with a very strong image of the sun, for instance, and we saw on the even on the upward. Okay. Yeah. Sorry. Oh, the stars. That's a good point. I think it's if I remember well what I did with this plot, there is the anti-solar point in there. So basically, telling you, because it's the upward flux, so it's where the image of the sun would be, the maximum in the radiance distribution would be in the upward flux corresponding to the direct sunlight. But the white circle, the white circle is telling you it's about it's the critical angle, sorry. So the critical angle being this angle above which an upwelling radiance is not going to be able to escape the oceans, because it's going to be fully reflected at the interface. So that means basically this white circle, what is within this white circle, is all the radiances that are going to get out of the water and that you can observe from space. So when you look at this distribution from a remote sensing perspective, everything which is outside of the white circle here doesn't matter. This light is not going out of the water, okay? Yeah, which is making the life of remote sensing, if I can say, a bit easier, because as you can see, within this circle, there is still a significant variability of the upwelling radiance, but it's definitely much less than what you include the entire upward hemisphere. Let's keep this one. Okay, but these three examples were, how historically people have tried to get to this full radiance distribution, but most of the time that's absolutely not what we do, because that's a bit complicated, developing this kind of very specific instrument. So what we do most of the time is what you have on the slide, and those of you who have been using instruments like this know what it is. So basically, we measure the radiance, the upwelling radiance coming from a single direction, which is from nadir. That's what we do. And then for the rest, we try to infer what the rest of the distribution could be from modeling, basically. And the other quantity we measure is the downward plane irradiance at different depths. So that's typically what these profiling radiometer systems do. Or what instrument on fixed platforms like moorings do as well. And that's another example on the right side. So doing this, you end up with, okay, we're going to look at a few simple examples of these quantities in the spectral domain or as a function of depth. So here you have examples, a few examples of spectra of underwater upwelling radiances. So that's measurement taken 60 kilometers off Villefranche, so in the Mediterranean Sea at this Boussole site. So generally relatively clear waters. The different colors here are for different depths. So it's 1, 5, 10, 20, and 40. And yes, and the one on the left is for the chlorophyll of 1 milligram of 1 milligram of chlorophyll per cubic meter, sorry. Relatively high chlorophyll concentrations for the Med Sea. The one on the left side is clearer waters. So, well, what can you see here? Well, basically the maximum of radiance in the blue, that's expected for the clear waters you have on the right side, a bit less on the left side because there is a bit more absorption. The other thing is for the same depths, let's say 40 meters, the light blue. Of course, here you have definitely less radiances because there is more absorption by chlorophyll and so on. I guess this kind of things you start to know this quite well. We see the fluorescence peak at 680. Even for the relatively moderate chlorophyll of 0.24, you see this in the upwelling radiance spectrum. And of course, that's a log scale, so there is definitely this, and you know that the exponential decrease of light as a function of depth. That's for the, not too sure why I didn't put that. Well, that's the above water downward irradiance. Yeah. Okay. Vertical profiles now. So the spectra, that's the same plot as the one on the right side here, which is reproduced on the left. And on the right side, you have the vertical profile of the quantities at this 5 wavelengths from the near UV to the red. And okay, a few things here. Exponential decrease of light with depth, okay, and that's what we try to figure out on a plot like this because we put it on a log scale for the radiance and a linear scale for the depth. If it would be, then you don't have straight lines on this plot, okay? So if the diffuse attenuation coefficient would be a unique single quantity in a given situation, given set of AOPs, you would have a straight line on this plot, Okay, attenuation would be the same, and that would be a perfect line in the log space. That's not really what we see here. Well, it's nearly what we see in some case, but we see as well, here there is definitely a change of slope, significant change of slope in the red. But there is a bit of this as well in the blue and a different part of the profile. So that just simply tells you that the diffuse attenuation coefficient in that case, for the upwelling irradiance, but that would be similar for the downward irradiance, is not constant with depth. There are some changes, and that's basically due to the rearrangement of the light field, which is very quick from the surface, from just below the surface. And progressively, there is more scattering, more absorption, and the light field has a tendency to become less structured, and then the downward or the diffuse attenuation coefficient have a tendency to become a bit more constant when you get to depth. Except that's because this is depending on the AOPs as well. If there is a strong change in AOPs at a given depth, then you will have, of course, a change as well of the KD. And that's a bit what we see here, I think. If you look at the 443 nanometer band, the blue, around 50-60 meter, you see some kind of an inflection and change, and that's actually because there is a deep chlorophyll maximum there, which is not very pronounced, but which is enough to change the IOPs and change the KDs and everything. So of course, sometimes, quite often what the interpretation we have and what we say are for assuming that IOPs are constant, but of course they are not. I think it's enough for this slide. Yeah. Okay. Do we need to go any further? In some way, if we know radiances in all directions, and all, or at least multiple depths in the water column, plus maybe the distribution above the surface, which is quite a bit to get to, but let's assume we can do this. What else do we need? Actually, we don't need anything else. Okay, if we would be experimentally good enough that we have the instrumentation and everything to get this full radiance distribution, we can stop there. You don't need any other instruments to measure irradiances or whatever. You have everything there because you can integrate then this distribution in all sort of ways, calculate all the K coefficients. You have a full description of the problem. Of course, as we have seen just before, that's generally not what we do. We generally have only the nadir upwelling radiance and the downward irradiance at a number of depths. Yeah, irradiances. So what we have seen this quickly in probably slide. So the different ways to get to irradiance. So to the scalar irradiance, which is generally denoted with this little circle on the top, which is basically integrating all the directions. But that can be, again, it can be on half an hemisphere, so that can be the downward or the upward scalar irradiance or the full scalar irradiance. And the downward and upward plane irradiances as to whether you integrate over the upward and downward hemisphere again, and by taking into account the cosine of the incident angle of each of these radiances. So yeah, what's written here, the irradiance falling on the plane surface varies as the cosine of the incident angle. Well, that's the Lambert's cosine law. And the other important thing to keep in mind, differently from radiances, irradiance follows the inverse square law, which means that's the and that's what happens if you do a calibration in the lab, for instance. You have to know exactly the distance between if you increase the distance between your source and the measurement of irradiance, it will change as an inverse as a function of the inverse square of the distance. So we have seen how we can measure radiances. How can we measure irradiances? So again, depending on which one you want to gets to. So if you want to measure the plane irradiance, so then you will have this plane diffusing material to collect energy from all directions, and taking into account there the fact that the one coming from grazing angles are not going to bring the same energy. So well, that's the simple drawing you have on the left side. And if you want to measure the scalar irradiance, then you need a spherical sensor. That's what generally has to be used if you work on the photosynthesis, because you can imagine all these small phytoplankton cells randomly oriented in the water and receiving light from all directions. So in that case, you don't really want to know what's coming on the plane, but you want to know what would come on the cell from all directions. So that's the scalar irradiance, which would be the interesting thing the relevant thing to measure for this. And that's one point I wanted to make, because I have seen a number of times, spherical sensors being used on the deck, and that doesn't really make any sense, or plane sensors using the wrong way to derive power. So yeah, just keep this in mind. What's coming into the water is coming through the interface on the plane interface. So if you want to get power, the power above the surface to maybe then propagate it or use it to normalize or whatever in the logic of working on photosynthesis, you need a planar sensor. But then underwater, you need a scalar sensor. And well, there are just examples of instruments that everybody knows. Actually, if we would make a slide with most of the instruments that this community has been using in the last 30, 40 years, there won't be so many of them, actually. We have a few manufacturers, and they have had their the most popular instruments. So that's not such a hugely variable domain, I would say. Okay, the specific case of PAR, so photosynthetically available radiation. Well, that's the integration of radiation in the visible. That's the one we use for the photosynthesis study. And that's basically a number of, sorry, I need to do this. Excuse me for 1 second. Oh, no, I'm okay. Yeah, I understand. Yeah, number of photons in the visible per unit time on a unit surface. So you need a sensor with a cosine response. Well, depending on in which medium you want to get to this. Yeah, and basically the sensor response, the sensitivity has to be proportional to wavelengths. We'll come back to this later on. Okay, so far we have been speaking about, okay, measuring gradients, irradiance. And the question now is, what can we do with this quantity as they are? We can do a few things, as written here. Well, as we said, we can know how much light is available for photosynthesis. You can calculate the number of AOPs. You can directly use as well some of these quantities, like the water level gradients, for this vicarious calibration of satellite sensors. But there is not much more that you can do with this. Okay, and why are we a bit limited? It's because, of course, these quantities depend on the illumination conditions. Sun elevation, cloudiness, other atmospheric properties, RC interface. So there is a lot that's going on into determining what the radiance is going to be. But the other reason, the one we mentioned a bit before, is having an idea of this full distribution is very complicated. So that's where you need to start to combine these radiance and irradiance in different ways, normalize them, to use depth derivatives. Okay, you see me coming, that's all the AOP. So one of the first things you can do is to go to this normalized water leaving radiance, so LWN or NLW sometime, or there are a few notation that have been used in the literature. So at least that's a quantity that can be compared with standard measurement made in situ for whatever the sun zenith angle is, the view direction, atmospheric correction, and wave state occurred at the time. So it's basically expressed here. So LW is here, and you normalize by the cosine of the sun zenith angle. So you get rid of this effect mostly. TD is the diffuse transmittance of the atmosphere. So you want to end up with the radiance that you would have without the atmosphere. I put quotes because it's a bit more complicated than this. And the epsilon is for the normalizing for the slight change of the Earth's orbit along the year, which is making a slight change in the incoming solar irradiance, or the eccentricity of the terrestrial orbit. So that's the simplest way to get to the normalized water leaving radiance. But it's not what we call the fully normalized, because it's still ignoring what we call the directionality of reflectance, which is basically the fact that radiances coming out of the water are not the same in all directions. You don't have an isotropic field. So that's the other thing that needs to be taken into account, is this bidirectionality of the ocean reflectance. So if I read this slide, so that basically means that for given IOP and illumination conditions, radiance exiting the ocean has not the same value for all directions. So just repeating myself a bit. That depends on the shape of the VSF. So that's the connection with the IOPs. How diffuse the underwater light regime is. So they are the ratio between scattering and attenuation, or scattering by water itself to scattering by particles. And as well, how diffuse the incoming solar radiation is. And that depends on, again, the sun zenith angle, but as well the turbidity of the atmosphere. If you have a very clear atmosphere, or an atmosphere loaded with quite a lot of aerosols, the distribution of radiance, of atmospheric radiance, sky radiance is coming into the ocean is not going to be the same. So if you properly take into account this bidirectionality and you correct for it, then you can start to really compare things. Because you can imagine a purely, totally homogeneous ocean in terms of IOPs. A satellite swath going across this. From the start of the swath to the end of the swath, the sun zenith angle has changed. The sensor is looking at different view angles, and so the azimuth difference is going to change as well. So you will get a radiance field, which is, with some variability, even if the IOPs are purely homogeneous. And of course, you don't want to interpret this as a change in the IOPs, so you need to correct for it, if you can. And just a few examples, the LW at nadir and LW at a view angle of 45 degrees can be different by 10%. Okay, that's important if you don't correct for this. And yeah, another example on the bottom, LW, and that's a bit what I just said before. At nadir, when the satellite crosses the equator and when it arrives above Villefranche, or maybe above here, because we are no longer in Villefranche, will differ again by the same, 10%, something like that. And that's what is illustrated on this slide as well. On the left side with theoretical calculations, radiative transfer. On the right side is from this radiance camera that I showed you a bit before. Well, I think in the interest of time, I'm not going to go too much in details of this. But on the right side, the measurements, the left column of the measurements are the downward radiance field. So that's not the one we're interested in, of course, for the satellite problem. The right column, so this one is for the upward radiance field. Okay? And again, the white circle, remember that the critical angle, so for the remote sensing problem, only what's inside this critical angle matters. And on this slide, you can see that the variability is not huge. Well, the color scale doesn't help much as well, I guess, on this particular case to see the variability. But still, it's within this 5, 10, 15%. And definitely, we don't want to interpret this wrongly as a change in the AOPs. The one on the left is, two wavelengths, 442 on the left and 560 on the right. Sun zenith angle is 45 degrees. This one are a bit slightly more complicated to interpret, but you can see that there is this dashed line here, which is for a value of pi. That this Q factor, which is the ratio of upward plane irradiance to radiance in a given direction. So if the radiance field would be purely isotropic, we would have this Q value would be pi, okay? Would be like this. And actually it's not, it's like this big thick curve is showing you with value ranging from 1.5, 2 to 5, something like this, okay? And structure the lots as a function of the sun position and the AOP. Okay, that might be a bit confusing, but just keep this in mind. This bidirectionality of the reflectance is something we absolutely need to correct properly when we interpret satellite measurements, or even in situ measurements as well, by the way. And to do this, we need models, because we don't have the measurement of the full distribution, so we need models. And that's what has been done in particular by a series of papers by André Morel and Bernard Gentili from 1991 to 2002 to try to improve this modeling of the bidirectionality and to use this. That's what is used to, to correct for this effect in all the, the bodies, sentinel and processing. That's basically what is done. Okay, well, that's a bit the same stuff here. Yeah, maybe I can just show you this, the plot on the bottom right. That's because that's a good illustration. So all this, the curve, and it's for the normalized water level gradients in the blue for 43 nanometer. That's across a number of longitudes. So it's basically number of lines across a satellite swath. Okay, and the simply normalized values are on the top. The one with LW divided by the transmittance, the cosine of the sun zenith angle. You can see some variability, and then the plot on the bottom is exactly the same thing, but then with this bidirectional effect corrected. And you can see that all the curves are coming much better all together. That's just an example of the impact of this correction. Okay. So, apparent optical properties, that's where we were. Let me check how many slides. Yeah. Okay. Okay. So the idea with AOPs is to define quantities that can be relatively easily determined from in situ measurements without having to use overly sophisticated and difficult to handle instrumentation, and which are related to the quantities of interest, of course, such as AOPs and chlorophyll concentrations, amount of particles, all the geophysical quantities we are interested in. Okay, and that's what is said in the bottom. Okay. The other important point is to be useful, they have to be only weakly depending on the environmental conditions as well. Okay, so that's the plot we saw a bit before. Maybe it's at a different No, that's okay. That's the same, but this time it's the downward irradiance. And okay, first of these AOPs, or the diffuse attenuation coefficients expressing the exponential decrease in the water column. So that's simple to understand. ED, yeah, just a quick question. This is basically two nearly identical plots, but there is a very significant difference in these two curves. Here you have very, very nice continuous curve, and here you have something a bit messy, a bit noisy. I guess, well, you probably know the reason for this if you have been doing some measurement in the sea. This one has been done under overcast conditions. So whatever you have, an interface which is affected by waves and so on, the light field is very stable and you get this very nice data. As soon as it's a clear sky, you have all this slight variability and you have all this noisy. Yes, Shuba? Oh, yeah. This is the noisy data on the deep water just because there is no longer enough signal for the instrument to make any good measurements. Yeah. So you would basically stop using this and forget about this. There is no more any light there, so it's just instrument noise. Yeah. Yes, it's a single cast. Yes, it's a single cast. You mean yes? Yes.
There is an instrument that sets this.
Yes. Yeah, it's basically what we call the dark noise of the instrument. You would get the same if you put a cap on the instrument nearly, and you make a measurement. You would get this kind of noisy data. Yeah. Okay, and that's just to finish on this noise at the surface. It's a constraint, is what we have in the environment, and it's actually making the radiometry measurement at sea quite difficult because of this. Okay. So summary, AOPs, so the KDs, downward irradiance, and the diffuse attenuation coefficient for downward irradiance. You have a number of ways you can calculate it. The definition is always the same, but you can calculate it this way. You take very relatively small depth increment and you look locally at what the value is. You can look at values at two depths very much apart. That's maybe the second equation here. Just below the surface at 50 meters maybe, and you have an average KD over this entire layer. Another one which has been defined by Kirk at some point is an irradiance weighted KD. So anyway, just to keep in mind that definition of KD is what it is, but practically the way you are going to derive it might be a bit different. That might depend on what you want to do with this, what sort of application you have in mind, what you are looking at. And they will look in clear waters, at least, very much like this, with these relatively low values, of course, in the blue, strong increase toward the red because of the strong absorption of water itself. And if you would have relatively consistent values of KDs, depending on the depth range you use, here it's calculated from 0 to 5, 0 to 10, 0 to 20, or 0 to 40, relatively consistent in the blue. But then in the red, it's becoming completely different because of this very strong change of the KD index. Well, I can skip this. Okay. This slide is borrowed from Kurt Mobley's lecture, actually. That's kind of a summary of the pros and cons of using KDs. So positive points, so the Ks are defined as rates of change with depth. So in theory, you don't need absolutely calibrated instruments. That's one thing. KD is very strongly influenced by absorption, so correlates well with chlorophyll in KZ1 water. That's another interesting property. About 90% of the water-leaving radiance, the one we want to collect from space, comes from a depth, roughly speaking, equal to 1 over KD. That's called the penetration depth. So that's an interesting quantity to know. And the radiative transfer theory provide the connection between KDs and the AOPs and other AOPs. So they are quite interesting quantities. Just wanted to come back quickly on this. Be careful with this kind of statement. Yes, in theory, because it's a relative, it's a rate of change. So if your instrument is 20% off, that doesn't matter too much. But there is not only this, the way your instrument is, your collector, for instance, is responding to the structure of the light field might change significantly. So maybe when you are close to the surface, your diffuser is doing a very good job in collecting all, light from all directions. And maybe when you get to the 50-meter depths, where the light field is structured a bit differently, you would have an error, which is a bit different because your collector is not doing exactly the same in terms of integrating light from all directions. So it's not only the calibration is not only in terms of how close your instrument is in absolute values to what should be measured, but how it's responding to the light field you are measuring. So temperature effects might play as well. So it's a statement which is basically true, but it's always a bit more complicated than that, I guess. And again, we will come into this tomorrow with the uncertainty. Negative points, KDs are not constant with depth, even in homogeneous water. The greatest variation is near the surface, and it's difficult to compute derivatives with this kind of noisy data you have seen before, for the downward irradiance. So you need a bit of pre-processing, filtering, fitting, whatever, to get to something. Otherwise, if you calculate KD on small depth increments close to the surface, you will get a noisy result with very large KDs, maybe negative KDs, and all sort of things. So that makes things a bit complicated. Okay, of course, we KD, but you can replace the ED by E0, LU, whatever, and you will have this other K functions. This one, yeah, okay. Maybe, yeah, can go through it anyway. This one is the irradiance reflectance, so another of these AOPs. It's no longer much used, actually. Most people use the remote sensing reflectance because it's what we get from space agencies. That's, again, this EU upon ED, often and generally defined at the 0- level, just below the surface. And this plot is just an illustration of how this big capital R is varying with chlorophyll, from the bluest to the greenest waters, with decrease in the blue, increase in the green, and so on. That's the basic stuff. And that's, the one which has been used to derive all these OC4, 5, 6, whatever algorithms. That's MODIS, Sentinel, VIRS, and so on use. Basically, ratio of irradiance reflectance or ratios of remote sensing reflectance as a function of chlorophyll, and that's what you have on this plot. And the algorithm is just basically generally the fit into this data. So RS, we just mentioned this. contrary to the big R, which is defined under the surface, RS is defined above the surface. So it's water leaving radiance divided by the incoming solar planetary radiance. So it has a very similar behavior anyway and use than R. RS is, however, slightly less depending on the environment and environment condition than R is. So that it's a bit closer to what could be an IOP nearly. Okay. And well, this plot is just an illustration of the huge variability in this RS spectra that you can encounter in the oceans and in coastal water. Nothing new, I guess. For the average cosines, they are not necessarily used very often, but they are still interesting and useful quantities. And they basically tell you, how far from being isotropic the medium is, basically. So that's the ratio of the ED upon ED0 for the scalar irradiance, or the same, but for the net irradiance. Okay, but we don't need to dwell on this. Okay. The use of AOPs, well, the K functions, mostly to know how much light you have at any given depth, and in particular for photosynthesis applications. You can use that as well to know how much heat is absorbed at any given depth. That's for the physics. So, and it has been very slow in the modeling community for them to start to consider that they had to use the model this heat deposition in the top layers as a function of the IOPs. Most of the global GCMs and mixed layer models and so on were using very crude parameterization of this until they realized that's the impact of varying transparency, basically, on how the heat is deposited in the top layers of the ocean had actually a significant impact on their models. And of course, the reflectance, that's what we use mostly to quantify stuff from space. So chlorophyll, sediment, lifts, whatever. And I think to nearly conclude this, yes, I have to conclude. So now how we go back from AOPs to IOPs. You remember when I told you a bit before, if we would have the full radiance distribution in the water, different depths and so on, we would be done. And we could use typically this equation, for instance. Well, this one is even simpler because you just need the ED, EU, and E0. So downward, upward, and scalar irradiance in the water column and their variability with depth. And from this, you can derive the absorption coefficient. That's really cool. There are other developments that have been proposed, and this one is not particularly recent, but there are a few others. And Mike Twardowski, who was with you this week, has proposed a number of things like this. So how to, again, calculate the IOPs from a different AOPs and radiometric quantities. So in that case, that was to calculate the back scattering coefficient. But quite often in this equation, there are a number of things we actually don't measure. So that's the difficulty of the problem. So are we really using this? Sometimes yes. Why? That's an example where we use this, this camera measurement. We had 2 cameras. We measured the full distribution at different depths. And we went through a full inversion, and we got some quite interesting results, actually. That's on the right plot here with the BB, mu, D, and absorption profile that we could derive from this. And the dark dot here and the dark profile here are the same IOPs, but measured independently with IOPs instruments. So That was kind of an interesting calculation. So you can do it. But, generally, again, the real world is we have LU at nadir, we have ED, we have a few of the K functions from this and RS. And that's a relatively poor description of the underwater environment, but that's what we need to do. So therefore, to develop numerical inversion of AOPs into IOPs, one has to include a number of assumptions, introduce simplifications or some empiricism, and to rely on radiative transfer calculations to build the inversion model. So just a few examples here. That's not something we will get into with very much detail. The first one on the top are these irradiance reflectance as a function of the ratio of the backscattering and the absorption to the absorption coefficient with this F factor in between, or the function of BB or A plus BB. And these F and F prime coefficients they are not constant, of course. They depend. That's where all the complexity of the problem is summarized. They depend on the wavelength, on the geometry, and on the IOPs. So that's where, and that's one of the approach which is possible. You use radiative transfer. You set up this with IOPs that you think are supposed to be the more realistic as you can, and then you can derive this F and F prime, and then from reflectance you can try to get to the IOP. The next one is an expression combining KD and UD. And if you combine all these, you can, for instance, have this equation on the bottom equation here. But again, this UD F prime will have to come from radiative transfer calculation. This one, yeah, that's just simply a slightly more complicated way of doing this. It's again at the top here. It's the Gaussian, what we call the Gaussian equation, by the way, from which you can derive the absorption, and then try to get to when you know one of the IOPs, you may be able to derive the other. And of course, then there is the more sophisticated way to do this with what we call this semi-analytical algorithms or semi-empirical, where you want to put the emphasis into the different parts of the different assumptions behind these models and these algorithms. So there are plenty that you probably know, the GSM, the GIOP, and so on. And they are used to propose some IOP products by space agency. And again, while that's becoming a bit more complex, you have an equation here on the bottom because, of course, they try to express the IOPs in terms of their different components. And because you start from a set of AOPs at a set of spectral bands, that's what your satellite is going to provide, RRS in a different number of bands, or the same from your in situ system. And then you need to constrain the system because you have a number of independent information in input, and you want to derive some of these parameters. So you have always some of these limitations. Okay, few last things. So that's good because it's time to conclude. Yeah, I didn't mention at all polarization. That's a domain in its own. Very few people do measurements of polarized radiances in the oceans. There is nearly no instrument to do this. If you want to do this, you have basically to develop your own instrument. But some have been doing this, and the idea behind this is because polarization, or the degree of polarization, depends on size, distribution, shape, and index of refraction of particles. So you may think, okay, if I can do comprehensive measurements of the polarization, maybe I can get back to this property. The other thing is the reflected solar light at the RC interface is polarized and can be eliminated by using some appropriately oriented polarized filters. So that's another, that's more an experimental advantage. And yeah, well, you can play with this, you know, when you do radiative transfer, you can use codes which are indeed taking into account polarization fully, others that ignore it. And yes, the thing you have just to keep in mind is you will get different results actually, even on the non-polarized quantities, okay? Up to a few and maybe up to 10% sometimes. Well, I think I'm not going to go more into polarization, but that's just yeah, that's a bit complicated. We don't really have the time. And the last thing I wanted to mention, it's a bit anecdotal, but it's an interesting thing to know. It's what is called the asymptotic regime. So it's a bit theoretical because that's not something that can be really easily measured. But it's said that at multiple optical depths in the water column, the shape of the radiance distribution in relative terms becomes invariant, okay? So it's constant azimutally and depending only on the absorption and scattering properties. So that's an interesting thing to consider because you mentioned radiometric quantities, it's the radiance distribution, so AOPs, but actually it's becoming an IOP in some way because it's becoming completely invariant and independent of what's going on at the surface and depending only on absorption and scattering properties. So this distribution becomes an IOP in that sense. And the kind of distribution is what I have tried to figure with this blue plot on the left side, which is kind of a bit weird anyway, but the upwelling radiance would be between about 2 and 4 orders of magnitude lower than the downwelling radiances, depending on proportion between molecular and particular scattering. Anyway, and as far as I'm aware, that has never been, it's a purely theoretical result from radiative transfer. It's never been really measured because you would have to go to many optical depths in the water column. And then, of course, you're left with very low light, not many photons there. And there is not really any instrument which is capable of measuring this. So anyway, that's a bit anecdotal, but I wanted to mention this anyway. And oh, yeah, sorry, there's still one. Another thing which is of growing interest, and there are more people now trying to work on this, is the light at great depths. Most of us are interested by what's happening in the aphotic layer, basically at the surface, when there is significant light, because we, are interested by the remote sensing problem, photosynthesis, and so on. But there is actually still light at significantly greater depths than what we are considering in this community. And there is life down there. And actually, there is an interest now to try to understand a bit better the impact of this. So that's what is said on this slide. Essentially, all field measurements of radiometric quantities are performed within the upper layers. We often use the 1% light level. In geometrical depths, generally, we go to 150 to 1 meter, and that's it. But there is still light deeper, so that's what I just told you before. So there is more interest now to do this, but of course you need to develop, again, that's not something you will get to with the commercial instrument. You need to develop a special prototype with very sensitive detectors. And now some people have been getting some good measurements, even down to, for instance, 440 meters. So that's an interesting developing domain. And you have this interesting nice little fish on the right side. Well, that's a depth, that's at depths where there is quite a lot of bioluminescence happening as well. So it's a combination of some remaining photons from the sun and some light generated by bioluminescence. Yeah, okay, that's it